So let us consider a real number, set of real number. So set of real number means you know that it contains natural number, whole number, natural number, then integers, so negative numbers, negative, positive integer, negative integer, then rational number, that those can be represented by p by q form, and also irrational number. So combining all those, then it form as a real number. So this real number we usually denote by this line real. So this is 0, 1, 2 like this. This is -1, -2 like this. So we usually denote like this. Now in this real number we want to take some subset. So you can consider, suppose A is a 0, 1, this subset, okay, and this sigma field generated by A, suppose this 0, 1. So what is the sigma field generated by this? So because we already discussed it, so this is if you consider whole R, suppose whole R, because we need to satisfy these three properties. So these three properties, S has to be in the class of subset. If any element in this subset, in this set C, then this complement also has to be part of this set, and any infinite collection if you have in C, then union of this countable infinite, union of this AI also has to be in C. Now if you consider S equal to R, it is a infinite, because all those example what we discussed up to this, here you can see that it is finite set. So that is why you can say power set contain 2 to the power n number of elements. But if it is a infinite like real number, or even if you take the interval 0 to 1, so then it is a countable infinite. So if you consider the power set, it is huge. So we cannot just count it, just you cannot say 2 to the power n type of things. So it is not a finite. So we represent it by some cardinal number. So cardinality. So this is kind of some different concept. So then we do not want to go in that complex. So that is why we want some particular sigma field that is actually useful for us. So here if you consider the sigma field here, sorry, yeah. So here we are considering this set R, and then we want to consider all subset of so sigma field generated by this element 0, 1. So then by properties 1, it has to be, this set has to be here R, then its complement also, so that is nothing but the null set. Now this set also here, because we are saying sigma field generated by this set A, so then it has to be here. So then its complement also has to be there. So that is nothing but 0, 1 complement. So then you can see that if you take the union, then it will be R. So this is the smallest sigma field generated by this set A. So this is a sigma field. Now if you consider some special, because we need to some more subsets are there in real line. So let us consider sigma field generated by, suppose A and B are two real number, any real number such that A is less than B, sorry, A is less than equal to B, some real number. Now consider a sub collection, suppose let us denote some C. This is nothing but all A looks like this, such that A be a real number, A less than B. Suppose if you consider this collection, and then you take sigma field generated by this C, all real number. So suppose let us denote this is C1. Now another collection we can take C2. This is suppose minus infinity to x, such that x is a real number. So now let us consider sigma field generated by C2. Now we will not go through more details about it, but it can be proved that even if you can take open, both open, or this closed, this open, like that, any of this, and then you take the sigma field generated by C1, and if you consider sigma field generated by C2, then this sigma field will be same as this sigma field, because all collection, all this set, it will be included by sigma field generated by C2. Here also all collection, whatever you have to include complement, you have to countable union, all these things you have to include. So then you can see that both sigma fields are same, and this kind of sigma field, it is known as some, it has some known name. So this sigma field generated by C2, it is known as some Borel sigma field. Borel sigma field. Okay. So this Borel sigma field contains all the intervals. So all half open, half closed intervals. So even minus many to x intervals, all this. So this is called the Borel sigma field. So sigma field generated by, so this is denoted by, suppose the script B. So let us denote it by script B. It is nothing but Borel sigma field. So in particular, so it is very useful. We will see that how we utilize this concept Borel sigma field. So because all kind of set you can think, most of the cases it will be inside Borel sigma field. There are some few, it is not Borel, we say Borel, not Borel measurable. So there are some Lebesgue measurable, not Lebesgue measurable. We are not going in details in that direction, just to understand the basic things. So now if you consider a sample space, now we are going back to the our concept of sample space. So random experiment, then you have a sample space. This sample space, it may be any abstract set, it may not be set of real numbers, subset of a real number, it may be anything, and then you have a collection of subset of S that form a sigma field, Then you have this collection, that is actually your space. We say it is a probability space whenever we are defining a probability on that. And now in that again in the real number system, we have a real number, and then we have real number, and then we have Borel sigma field. So we want to relate these things, two things. One, in the left hand side, it is our usual sample space and some collection of subset of S that form a sigma field, and the right hand side we have the real number system and the Borel sigma field, and we want to relate by a measurable function. So that, so measurable function, that we want to relate by a measurable function. So this x is to the set of real number. So a function, a measurable function. So till now whatever we defined measurable function, I hope you have understood it, or you can go back and go through again. So what is measurable function? So there are two sigma field, S1 F1 and S2 F2. S1 is a non-empty set and F1 is a collection of subset of S1 satisfying some properties, that is known as sigma field, and S2 again another non-empty set, and F2 is a collection of subset of S2 that form a sigma field, be the two sigma field, and a function S1 to S2 is said to be measurable function if for any B belongs to F2, F1 of B belongs to F1. So that means in this, so here also if you consider any, so Borel sigma field means it contains, at least because it is generated by this kind of sets. So also this kind of sets also there, you can see that taking intersection, complement, all unions, all these things, you can see that any intervals is there. So any singleton set also there, you can check that. So if you take the intersection like closed interval, this complement if you consider that is there, if you take union, that is there. So in that way you can show that some singleton sets also there. So singleton some number 1, 2, 3, 4 also inside this Borel sigma field. Now if you consider a measurable function, a measurable function x S2R, okay, so 1 minute. A random variable, so we want to define a random variable. So random variable as, so let us recall again S and C, so it is a sample space and collection of subset of S, that is sigma field, and R is the set of real number and B is the Borel sigma field. So Borel, it contains the Borel sets. We say that all the elements in this Borel sigma field, it is nothing but the Borel set. So a random variable, a random variable x is a measurable function from S to R. So basically x is a measurable function, R, that is a S to R. So it is a Borel measurable, we say. So what is Borel measurable then? So any set you take, B belongs to this Borel set, x inverse of B, it must belongs to the C. So this is x, and so sample space S and collection of subset of S is C, that is a sigma field, and then B is a Borel set in B. So x inverse B, it is nothing but in C. So then it is known as, so then it is a measurable set. So measurable function, x is a measurable function, then it is called the random variable. So now let us discuss some of the random variables, some numerical example, some of the example of random variable. So let us consider one random experiment. So suppose very simple experiment, tossing a coin. Now what is the sample space? S is nothing but head and tail. So now we want to take suppose sigma field like C is the power set. So we discuss the power set, phi, it is S, then H and T. It contains all the subset of S. Now we can define a function, suppose x, whenever so x is a function, suppose x of h, x is nothing but S to R. It is a function from S to R, and defined by x of head, this is nothing but x of head, this should be a point. So here this is the S, it contains 2 points, head and tail, and here is some real number. So real number is like this, 0, 1, 2, minus 1, minus 2, this is. Now I want to map this on, we want to define a function. So just a simple one function I want to define. So x of age is equal to 1 and x of tail is equal to 0. Just I want to see whether it is a random variable, it is a function. First of all, it is a function, well defined function. Now for random variable, because for showing it is a random variable, it is enough to show, because we have told that any Borel set you have to consider. Borel set means sigma field generated by all such set. So it is enough to show that if this inverse of this set, so that means if you, because obviously this kind of sets are there in the Borel set, because it is sigma field generated by this set. So let us consider one set Borel set. So let us consider one Borel set. Suppose B is a set, it is nothing but minus, it looks like, so any interval you can take or any, so let us consider minus infinity to x, one x is a real number, so any number. So suppose for simplicity let us consider one real number, like suppose it is minus 2, okay, minus infinity 2, so this is a closed interval we will take. So then what will be x inverse of B? X inverse of B. So x inverse of B is nothing but all x belongs to the S such that x of, basically see that x of x should be belongs to B. This is the definition of a x inverse of B. So, it is a inverse of this set. Now, B we have considered this. So, it is nothing but same to say that because x belongs to B means it has to be less than equal to. So, x has to be less than equal to minus 2 because it is closed and greater than minus infinity. Okay. So, that is we have to check. So, then what are those points satisfying this relation, because x of age is 1, x of t is 0, any elements in S is there who is satisfying this property, this x is less than equal to 2? No, because x of head is 1 and x of tail is 0. That is why this is nothing but null set. So, null set is inside C. So, this is true for any other value also. Let us consider another set. Suppose another set B2, it is nothing but minus infinity to suppose 1, or we can take some 0 or any real number, suppose 0.5, any real number. So, it may be irrational, any number. So, minus infinity is 0 to 5. So, then what is x inverse of B2? X inverse of B2 is nothing but all x belongs to S such that x of x belongs to B2. Now, what is that? B2 means this set. So, all x belongs to S such that x of x greater than minus infinity less than equal to 0.5. So, then our what is our mapping? So, how it is function? X of head is 1, x of tail is 0. So, then you can see that the number, what x of head is 1. So, it is not satisfying by head, x of tail is 0, only 2 points are there in S, we have to check, x of tail is 0. So, it is satisfying by the tail. So, this is nothing but this tail. This is also subset of, so this is also belongs to C, this is also belongs to C. So, in this way if you consider, you can see that not only that, any other Borel set also. So, then any other Borel set how it is looks like, suppose in a singleton set. So, we have some kind of notation. So, this notation is like suppose x is equal to 1. So, what is this notation? So, this it is defined as, it is denoted as all x belongs to the sample space S such that x is equal to 1. For this example, what is that things? Because x of head is 1, so this is nothing but only head. So, then this is also in the collection of sigma field, this C. So, we denoted this by C. C is nothing but this power set. This is also inside C. So, similarly we can, so this has some kind of notation, x is less than equal to suppose 1. So, this notation how it is denoted by this. So, all x belongs to S such that x of x is less than equal to 1, and whenever in the left hand side no nothing. So, that means it is greater than minus infinity. So, this is nothing but what are the value it is satisfying, because x of head is equal to 1, and this include less than equal to 1 also, x of tail is 0. So, it includes t also, it includes head also. So, that means it all in the sample space. So, basically null set also there, because null set nothing, and also whole. So, basically it is nothing but so yeah, so only these two, sorry, no, 1 minute, we should not denote like this, because it is the point in the I just here I wrote like it is only one set containing those point, head and tail and head are there, which is nothing but the whole sample space S, and which is a subset of S, and this belongs to C also. So, you can see that. So, basically this collection what we took. So, here it is C2 basically this is looks like this. So, the x, if you consider C2 is nothing but all minus infinity to x such that x belongs to the real number, and Borel said is we told that this is we just mentioned that sigma field generated by C2, and this is nothing but, so any set if you take like this and take x inverse of this, it is nothing but same as this notation x less than equal to x, because both has the same meanings. X belongs to S such that x is less than equal to 1 minute. So there is a confusion, so sorry. So yeah, so because we are denoting this x here in the real line, so we need to use some different notation. So otherwise there will be a confusion. It is better if you take this notation, because x we took as a real number and any s belongs to s as a any element in, suppose let us, okay, so we need to erase many things. So just few things, let us here we correct it. So because x is element of s, so this is better that we denote by s here, so that small x we are denoting as by a real number. So now if you consider this kind of set, so C2 we consider this set minus infinity to x such that x belongs to real number, and this B is nothing but Borel sigma field generated by C2, which is nothing but the Borel sigma field. Then what is x inverse of minus infinity to x? So this is nothing but all x, so all, that is why this is the confusion, all s belongs to s such that x s is less than equal to x greater than minus infinity. So again if you denote this notation x less than equal to small x, this is also nothing but, see that this notation all s belongs to s such that minus infinity to less than x of s less than equal to s. So both are same. So basically this is nothing but, so this is nothing but x less, it is just a notation only, simplified notation. X inverse of minus infinity to x is nothing but we are denoting by x less than equal to x. Okay. So what we understood now? So let us, from the beginning we started a random variable